All right, in this video, we're going to talk about the central limit theorem for means. So hopefully you watched a previous video where we went over the central limit theorem for proportions. This is very similar, except for instead of measuring proportions, we're going to be measuring means. So just a quick little recap. What's a sampling distribution? So the sampling distribution of a mean is the distribution, histogram, of sample means that are collected from all possible samples from your population. Okay, so you take a bunch of samples and you calculate the mean of each of those samples. For example, imagine if you're sitting in a class with 30 students and you're asked to partner up with your neighbor, so you have groups of 2, so now there's 15 groups. Each of the 15 groups is asked to calculate the mean age within that group. So now you have 15 data points there, right? So the collection of all possible samples like that is a sampling distribution of the means. So what we want to see is what we saw before is that, so consider these histograms here. The central limit theorem says as the sample size increases, we're going to notice that our distribution, our sampling distribution, becomes normal, approximately normal. So what you can see here is that with the histogram with size 2, we see that that's a fairly right skewed distribution there, right? But as the sample size increases, as it goes from 2 to 4 to 30 to 100, we see that we have a clear normal distribution. And we also notice that the variability becomes smaller. The normal curve itself becomes skinnier or tighter. Okay? So that's exactly what the central limit theorem is. It says as the sample size increases, the sampling distribution becomes normal. Okay? All right. So central limit theorem states if certain conditions are satisfied, then the sampling distribution of means becomes approximately normal with a mean equal to mu and a standard deviation equal to this interesting looking formula. It's the standard deviation divided by the square root of n for a large enough sample size n. Okay, so as I denoted here, mu, that is your population mean. So it turns out that the mean of your population will be the same mean of your sampling distribution. And sigma is your population standard deviation. So, but whenever it comes to calculating probabilities and things of that nature, with a sampling distribution, you're not going to use just sigma, you have to use your standard deviation divided by the square root of n. That's the difference between working with just a single maybe value versus working with a distribution of samples. Okay? So what are these conditions? The conditions are pretty straightforward from what we saw in the last video on proportions. Independence. We need our values to be independent, or we need our data, our samples to be independent. Okay? So once again, that independence assumption is something that you can't readily validate or verify, but it's just something you have to look at the situation and say, okay, because this outcome won't affect the other outcome, we are independent, right? Once again, if I'm calculating mean ages of students, right, it's assumed that the students are independent, they're not related to each other, right? So once again, that's an independence assumption. Also, if we're taking random samples, there's a randomization condition. If you take random samples, that automatically means you're independent. Okay, so random samples, randomization is one thing you want to definitely check for. Also, the 10% condition, this should look familiar as well from the last video. We should be sampling less than 10% of the population. If we sample too much of the population, we're going to get into some dependent situations. And lastly, the general rule of thumb, lastly is that we need a sample size that is sufficiently large. Folks, I would love to be able to tell you that there is a cut and dry number that you should look for, but that's not the case. Sufficiently large depends on really the situation, the skewness, right? If we start off with a very skewed situation like we kind of saw in this example here, we notice that it takes quite a few sample size for us to start to become normal, right? It starts to happen around 30. So the more skewed you are, the more sample size it takes, the larger your sample size needs to be in order to see that normal distribution. However, if you start off with a distribution that's not as skewed, then it will take less of a sample size to get you to a normal distribution. Okay? But the general rule of thumb is that if you have a sample size that's larger than 30 or 40, that's usually pretty sufficient. All right? So that's a quick rundown of the central limit theorem. If these conditions are met, then we say we have a normal model where the mean is equal to mu and the standard deviation is sigma divided by the square root of n. That's what this is. All right, let's get into some applications of the central limit theorem. So a college physical education department asked a random sample of 200 female students to self-report their heights and weights, but the percentage of students with body mass indices over 25 seems suspiciously low. First of all, I think that's kind of rude for them to be asking for heights and weights. Anyways, one possible explanation may be that the respondents shaded their weights down a bit, so they lied. The CDC reports that the mean weight of an 18-year-old woman is 143.74 pounds with a standard deviation of 51.54 pounds. But these 200 randomly selected women reported a mean weight of only 140 pounds. Okay, so that's the background information, a lot of information there. What we want to know first of all is, are we able to apply the normal model to this sampling distribution of mean weights, aka check the conditions? All right. Well, first of all, let's talk about independence. Let's talk about independence. Because the students were sampled randomly, right? Random sample. Because we have a random sample, we have randomness, which means, yes, we are independent. Okay? So the independence comes from, once again, the randomness. All right? Next, we need to check if we have the 10% condition, right? So did we sample less than 10% of the overall population? Certainly we did that. 200 female students is certainly well less than 10% of all female students in the world, right? So we have less than 10% of the population. So yes, we have the 10% condition. And lastly, are we large enough? Is the sample size large enough? And the answer here is yes, for a couple reasons. First of all, 200 is a pretty substantial sample size. And also, too, if we think about it, in general, population weights kind of follow a normal distribution anyways. So even if we had sampled like 10 female students, I think we would still be okay because we're coming from a normal distribution already. So the central limit theorem really says if you don't have a normal distribution or if it's skewed, then that's when you really need a lot of samples. But because weights are already kind of normally distributed, 200 is certainly more than enough. Okay? All right, so all the conditions are met and we are able to apply the normal model here. Okay? Let's go down to part B. Draw the normal model for the sampling distribution and indicate the 68, 95, 99.7 rule on your model. So we've seen this a couple times. We know 68% is within one standard deviation. We know 95 means 2 standard deviations. And we know 99.7 means 3 standard deviations. But we'll get to that in a second. First of all, we need to grab the parameters of our normal model. And by parameters, I mean the mean of our sampling distribution and the standard deviation of our sampling distribution. Okay? All right, so the central limit theorem tells us if all the conditions are met, then the mean of the sampling distribution is the same as the mean, the population mean. So just once again, I want to show you guys. If we come up here, that's it right there. That's the rule. The mean of the sampling distribution is the same thing as the population mean. Well, what's the population mean weight according to CDC of 18-year-old women in college? Is 143.74. Okay. The standard deviation of our sampling distribution, of our sample means, will be the population standard deviation, very important guys, divided by the square root of n. That's what makes this different from just a normal model we talked about earlier in the semester. So we take our standard deviation, which is 51.54, and we divide it by our sample size of 200. Remember, there were 200 randomly selected women. So we do 51.54, and we divide it by the square root of 200. Okay, and what is this going to give us? Let's go out to 2 decimal places. So I'm going to go to my calculator here. I'm going to do 51.54 divided by the square root of 200, and we get 3.64. Okay. All right. So what's the normal model going to look like? It's going to be as follows. All right, so what we have here is a distribution of sample weights, mean weights. That's why it's X bar along the horizontal axis here. Right down the middle is our mean. We said the mean was 143.74. This is the mean of the X bar, okay? Next, we're going to have one standard deviation to the left and to the right. So let's come over here. Let's call this one standard deviation to the left. Let's call this one to the right. How do we figure out these values? Well, we take 143.74 and then we add 3.64. Okay, so I'm just going to do this in my calculator off screen here to save a little bit of time. But if I add those two standard deviations, or those values together, we get 147.38. Man, I cannot write today, I'm sorry. 147.38. Once again, this was found by taking 143.74 and adding one standard deviation of 3.64. Okay? And the same thing can be found by now subtracting. All right? So we're going to do, let's see here, we're going to do 143.74 minus 3.64, and we get 140.1. Okay? All right. So just to remember, this is 1 minus a standard deviation. This is, or your mean minus 1 standard deviation. This is your mean plus 1 standard deviation. And we know that from here to here, let me do a different color. We know that from here to here, we have 68% of our data. Okay? All right, next let's go out 2 standard deviations. Okay, so that would be out here somewhere. And then out here. So now what we do is that one, let's go to the right one, that 147.38, if we take that and add to it another standard deviation of 3.64, that will give you 151.02. This is, once again, this is our mean plus 2 standard deviations. And then if I do 140.1 minus 3.64, we get 136.46. And this is our mean minus 2 standard deviations. I know that's cramped handwriting, but hopefully you guys see the pattern here. All right. And then lastly, if we go out 3 standard deviations to the left and to the right, let's see, just add on another standard deviation to the right, subtract from the left. So I'm going to do 151.02 plus another 3.64. And we get 154.66. And if I subtract 3.64 from that 136.46, I get 132.82. And this is the mean minus 3 standard deviations. This is the mean plus 3 standard deviations. Oh, and I forgot. So, and then remember, if we're going out 2 standard deviations, that tells us 95% of the data. And then if we go out 3 standard deviations, that will give us 99.7. Okay. 99.7. All right. So that is our normal model there, folks. Okay, moving on. let's see. There we go. Does the mean sample weight of 140 pounds seem unusually low? All right, anytime they talk about unusual, folks, this is our key that we need to find a z-score. Because remember, more than 3 standard deviations from the mean means, no pun intended, unusual. Okay? So we're looking for a z-score. If our z-score is more than 3.0 or less than a negative 3.0, remember z-score could be positive or negative, that means it's unusual. So how do I find a z-score for a sampling distribution? Well, here is the formula, right? Z-score is always your data value. So what's the data value in this case? It's the sample mean from those 200 women minus the mean of the sampling distribution divided by the standard deviation. And we have all of this information, right? So what was the mean weight for the 200 women? It was 140. So we're going to take 140. Sorry, went too far there. We take 140 minus the mean of the sampling distribution, which is the same as the population mean. We said that was 143.74. And we divide it by the standard deviation for the sampling distribution, not just the regular standard deviation, but the standard deviation sampling distribution. That's why we use 3.64. Remember, that was our standard deviation for our sampling distribution. All right. So now I will show this on camera. Let me calculate this z-score. All right. So I'm going to do open parentheses, 140 minus 143.74, I believe. All right. And then divide that by 3.64 was our standard deviation. And we get into 2 decimal places, we get a negative 1.03 as our z-score. So that means, remember, I need to be smaller than a negative 3 or bigger than 3 to be unusual. Negative 1.03 indicates it's not all that unusual. A sample mean of 140 pounds is not unusual. So that is our answer. A sample mean of 140 is not unusual. That's because my z-score is not exceptionally big or exceptionally small, okay? Remember, for unusual, the z-score needs to be smaller than a negative 3 or the z-score needs to be bigger than a positive 3, okay? All right, so moving along here, another example, last example. The Center for Disease Control and Prevention reports that the mean weight of adult men in the U.S. is 190 pounds with a standard deviation of 59 pounds. So apparently I'm fixated on weight. An elevator in our building has a weight limit of 2,500 pounds. Assume 10 men get on the elevator. Check the conditions and describe the normal model for the sampling distribution of sample means here. Okay? All right, so let's talk about this. So we need to check the conditions for this scenario, right? Okay, so let's check for independence. Okay. Well, we can, once again, checking for independence, guys, it's nothing you can verify. It's just an assumption. But we can assume that, 10 men getting on this elevator is pretty random, right? So we can say that having 10 men on the elevator, it's reasonable. Having 10 men on the elevator, it's reasonable to assume randomness, right? Okay, so because of that, independence is good to go. Okay, so once again, independence, It's nothing you could really verify. It's just something that, is it reasonable to assume that they're independent? Yeah, it's reasonable. Okay, what else do we need? We need the 10% condition. Remember, we have to be less than 10% of our population. Well, certainly 10 men is way less than 10% of all the men in the world, so the 10% condition is certainly good to go. And then lastly, is our sample size large enough? Okay, so you may ask yourself, you may say, hey, 10 is a pretty small sample size, and I would agree with you. But we have to think about the population weight distribution here. Population weights, if you pull up a histogram of population weights, they're going to look pretty normal. So the population is already normal, and we're sampling from that normal population. Okay? An analogy that I like to use in class is, let's say I had a classroom full of people with red hair. Since my distribution is all red hair, whatever sample I take from it will also be red. And so that's the same thing here, right? If I already have a normal population, whatever sample I take from it will still be normal. Okay? So large enough, even though 10 is small, because weights are normally distributed, large enough, we are good to go with just 10. If the distribution was skewed, if I had something, let's say we were talking about salaries of people working, right? That's a right skewed distribution. That's really right skewed. The longer you work, hopefully the more money that you make. So that I would need more sample size, a bigger sample size than 10. Okay, so we do have, we're not done. So we have a normal model. Okay, we have all the conditions for the normal model, and they need us to describe the sampling distribution. So to describe it here, I'm not going to draw the whole normal distribution. We're just going to calculate the mean and the standard deviation. So the mean of the sampling distribution is the same as the population mean. And they told us the population mean weight of all men is 190 pounds. So we're going to have a normal model with a mean of 190 and a standard deviation of, the standard deviation is 59 pounds. But we divide it by, well, let's write the formula. Let's be consistent. It's the population standard deviation divided by the square root of n. So it's going to be 59 pounds divided by the square root of, we have 10 men in that sample. So let's do 59 divided by radical 10. That gives us 18.657. Okay, so we have a normal model with that mean and that standard deviation. All right. What's the probability that 10 men will overload the elevator's weight limit of 2,500 pounds? Okay, remember there's a weight limit of 2,500 pounds on that elevator. So here's what we'll do. Here's the hint. For 10 men, for us to get to 2,500 pounds, we need a mean weight of 250 pounds per men, right? So if I take 250 times the 10 men, that's how I get to 2,500 pounds. Okay? So really what this question is asking, it's asking what's the probability that our mean weight, X bar, has to exceed or go over the weight limit, so it has to be greater than 250 pounds. Remember, once again, we have to take the 2,500 divided by the 10. That's how we get the 250. All right. So how do we do that? As we saw in the other video, there's a couple ways we can go about it. We can go the z-score route. Let's try that. So we're going to convert this 250 to a z-score. So to do that, you take your sample mean, which is 250, minus your mean of your distribution divided by your standard deviation. So we're going to take 250 minus, and I'm just going to write down just for the sake of my memory, which is going out. We had the mean weight was 190, I believe, and the standard deviation of the sampling distribution, we said that was 657. 18.657. All right, I just want to keep that there. All right, so then to get our z-score, we take the 250 all right, the sample mean. We divide that by the mean, the population mean, which is 190, and we divide it by not just the standard deviation, but the standard deviation of sampling distribution, which is 18.657. Let's see what that looks like. So open parentheses, 250 minus 190, close that up, divide that by 18.657. Into two decimal places, we get a z-score of 3.22. Okay? So our z-score is 3.22. So now, instead of finding the probability that x bar is greater than 250, now what we've done is we reduced the problem to saying, what's the probability that z is greater than 3.22? Which equals, well, we're going to use some technology for this, or feel free to use your z tables if you're comfortable with those, but I'm going to come over here to StatCrunch. Okay. Get my mouse here. All right, I'm going to click on Stat. I'm going to go to Calculators, and we're going to do the normal calculator. Okay. My mean, let's do it like this so you guys can see. I'm going to scribble this out. Well, because we're dealing with the z distribution, remember for z, I know this is confusing. For z, remember the mean is 0 and the standard deviation is 1. Okay, so we converted all that, we standardized all that stuff, right? So our mean is 0 and our standard deviation is 1. Okay, that doesn't look like a... okay, let's do 0.0. Okay, our mean is 0, and we want to know the probability that z, and our standard deviation is 1, and we want to know the probability that z is greater than, so we're going to select our greater than option, change that to greater than or equal to, is greater than or equal to 3.22. So let's scribble that out. Let's do 3.22. Okay. We calculate that, and we get an extremely small probability there, right? Because remember, more than 3, a z-score bigger than 3 is really unusual. And now you're seeing it. So to 1, 2, 3, 4 decimal places, just so we can get a non-zero number here, it's 0.0006. All right, 0.0006. All right. Or let's say you didn't want to do that. What we could do is we could go directly and use this information, right? We could say, oh, just go and say, we could use the 250. We could use the population mean and the sampling, or the standard deviation for the sampling distribution. So another way is we could have said, let me come back here. Our mean was 190. Our standard deviation was 18.657. Okay, and then now our value in here is we want to find the probability that x is greater than, it was 250. If we compute that, you see that we get, there we go. We get the exact same answer as before. Okay? All right. So I just want to show you a couple different ways of doing that, but either way, we get the 0.0006 is our answer there, okay? All right, moving along. So it's very unlikely, basically, that we're going to overload that elevator. What's the probability that the mean weight of the 10 men will be between 200 and 220 pounds? Okay, so let's convert that to probability notation. This is the probability that the mean weight is between 200 and 220 pounds. Okay. Now, what you could do, we could convert both the 200 and the 220 to z-scores and find the probability. Okay, we could do that. But I'm just going to do the shortcut. Instead of doing that, or we could keep the 200 and 220 and use our mean X bar being the 190 and our standard deviation being the 18.657. Right? Because remember, when you convert them to z-scores, remember here, your mean is going to be 0 and your standard deviation is going to be 1. Okay? So I'm going to do it this way, but feel free to do it either way. Matter of fact, why don't you take a second, pause the video, see if you can verify my answer using it the first way. But I'm going to go to 200 and 220. So we're going to go back to our StatCrunch calculator. My mean and standard deviation are the same, but instead of doing the standard calculator, I'm going to do the between action. Okay? We're going to do the between action. And so I'm going to come over here, and my lower bound is going to be 200. The upper bound is going to be 220. We calculate that. And to 3 decimal places, we get a 0.242. So hopefully, see, that way was a little quicker. All right, last one, guys. There is only a 10% chance that the mean weight of the 10 men is greater than what value? So the question is this. The question becomes, let me see here. Another way of kind of thinking about this question is looking at it from this perspective. We are trying to say the probability of X bar greater than some number, which we don't know, some sample mean weight, has to equal 10%. That's what this is saying. Okay? What is the mean weight that only 10% is greater than that mean weight value? Okay? All right. So the way we're going to do this is we're going to exploit the z-score formula. So remember, z-score is X bar minus the mean of X bar over the standard deviation, right? Okay. What I claim is that we actually have information for the z-score. We have the mean and we have the standard deviation. We just need to solve this equation for X bar. That's what I claim. All right. So how could we do that? Well, let's first of all talk about the z-score. Okay. In order to visualize that, we got to draw a normal distribution. Okay. And what we're trying to do is we're trying to find the z-score. Okay. So these are z's. We're trying to find the z-score that has only 10% of the area to the right of it. So this is the unknown z-score. But this shaded area needs to be 10%. Okay? So the z-score is not 0.10, but the z-score is going to have to be the z-score that has the area to the right of 0.10. Well, how do we find that? Well, we got to do like a reverse table lookup. So let's do that. Let me show you how to find this z-score. All right, so let's hop on over to some z-tables for this, okay? But before we do that, actually, remember that the z-tables give us areas to the left or probabilities to the left. So if I have 10% to the right, that means how much do I have to the left? I have 90%, 0.90. So what we're going to do is we're going to look at our z-tables. We're going to look for an area, a probability of 0.90, get as close as we can to that. We're going to back out what that z-score is. So here I've downloaded the z-tables from our course. And here I'm looking inside the table at these 4-digit numbers, okay? So what I'm hoping to find is a 4-digit number that's close to 0.9000. That's 90%. So I'm not going to get it with any of these negative z-scores. So let me flip over to the positive ones. And it's going to take a while for your eyes to adjust, but it appears me see if I can I highlight it? I'm not sure it's going to let me highlight here. But if you look and if you go, oh, there we go. Right there, I just highlighted. That's the closest value we're going to get to a 0.9000, 90% area to the left, okay? So what's that z-score? We back it out. So it's going to be a 1.28. Remember that top number, that column gives you the second digit. So the z-score is 1.28. All right, so let's keep that in mind. The z-score here is 1.28 that has area to the right of 10%. So now we know what the z-score is. We know what, so let's go ahead and fill in everything. So our z-score, actually let's do this. Let's do this. Let's go ahead and solve this equation. So what we're trying to solve for is this value right here. This is the unknown value. So what I'm going to do is I'm going to multiply both sides of my equation by the standard deviation. Okay, so we have z times the standard deviation of x bar, right? Order of multiplication doesn't matter, equals, right side cancels, I'm left with x bar minus the mean. And then I'm going to add the mean to both sides. And so that's going to give me my formula on how to find my sample mean value, okay? So it turns out that the mean plus the standard deviation, or excuse me, plus the z-score times the standard deviation will give us our unknown sample mean, okay? So what's that? We know that the mean is 190. Remember, mean of x bar is 190. So we take 190 plus our z-score, which we found to be 1.28, times the standard deviation. All right, let's put that in the calculator. So 190 plus, let's clear this out, 190 plus 1.28 times 18.657, 213.88. So what this means is that as we conduct this experiment a bunch of times, only 10% of those times will we have a sample mean weight of those 10 men being more than 213.88 pounds. All right, I believe that is it for this one. I know it was another long one, but I really do hope these videos are helpful for you. I'll see you in the next one.